Hello. In this video, I'm going to cover the MTA 98-366 networking fundamentals, and this will be the objective: understand IPv4 and understand IPv6. And so, let's take a look at IPv4 first. So, some of the definitions that we're going to want to know for IPv4. The first one is class full IP addressing. And so when we're talking about class full IP addressing, what we're basically meaning is that the default subnet mask for the IP address matches our standard subnet mask for that class, and it's broken down into octets. And we'll get into what that means a little bit more, but just so you know, so the class full IP addressing means that a class A address is going to have the subnet mask 255.0.0.0. A class B IP address is going to have the subnet mask 255.255.0.0. And the class C IP address is going to have the subnet mask 255.255.255.0. We're also going to talk about subnetting. And so subnetting is the process where we take a larger network and divide it into smaller networks, and we split this up using that subnet mask. And the reason is we can do that for security purposes, to isolate one group of computers from another. We can also do it for network purposes. If we separate out groups of computers, then when we have a broadcast situation where, say a switch or a hub or something is sending out a message to every device on the network, we can make sure that it goes to the devices it needs to and segregate out the devices that should not be part of that broadcast network. We're also going to cover classless interdomain routing, or CIDR. This is what would be our classless addressing. This typically, we're going to see this would be like it'd be a typical IP address, and then there'd be a slash and a number behind it. And remember, that indicates the number of binary digits from left to right that are included in the subnet mask. And this was originally, they came up with this in 1993 as a way to kind of reduce routing tables and try to slow down the number of IP addresses that were being given, because we were running out of IP addresses. Since then, we have developed the IPv6 standard, and so the CIDR addressing isn't as widely used anymore. Another term we're going to use is subnet mask. And so the subnet mask, it's a 32-bit number, and basically it's going to be split up into typically zeros or 255s for our class full IP addressing. And all it does is it kind of indicates to us which numbers we can use for an IP address in each range. All right, so this is what an IP address looks like. We're going to have four groups of what we call octets, separated by a decimal, or a point. And the reason we call this octets is because, so we see that each one of those, it's going to be numbers from 0 to 255. So if you ever given a question and you're asked to identify, is it a valid IP address, if there's a number above 255, or I guess we wouldn't see negative numbers, but obviously if there's something below 0, it would not be a valid IP address, because each one of these groupings, or octets, it's going to accept numbers, and then numbers need to be between 0 and 255. And the reason that we call this an octet is actually because it goes back to our binary numbering system. So as you can see, that octet is broken into 8 binary decimals. And so just taking this octet from the top, so we see the second octet is 12, and that actually would be represented in binary as 0, 0, 0, 0, 1, 1, 0, 0, and that would give us 12. And why would that give us 12? If you're not familiar or don't remember your binary numbering system, going from right to left, the first digit is our ones, The next digit is our 2s, 4s, 8s, 16s, 32s, 64s, and 128. And so having either a 0 or a 1 in each of those places gives us a different value. And the reason that we have 0 to 255 is because if you add up all these numbers, 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, that gives us 255. That is the largest digit that we can comprise in an 8 binary digits. When we're talking about class full IP addressing, these are how we break down our classes. So any IP address that has the first octet where the number is between 1 and 126, that is going to be a class A. That's going to be an address in the class A range. And the default subnet mask for a class A IP address is 255.0.0.0. And then we're going to move to B. An address in the B range is going to be from 128 to 191. And so any IP address that's in that range that is using a class full IP addressing is going to have the default subnet mask of 255.255.0.0. And then the class C is going to be an IP address where the first octet is 192 to 223. And if we have an IP address that's using class full subnet masking, that is going to give us a default subnet mask of 255.255.255.0. Some IP address ranges that we want to be aware of that are reserved. So the first one is going to be 10.0.0.0 through 10.255.255.255. So essentially, the whole of our of the 10 the octet, where anything with the first octet of 10, and that's reserved for our Class A private network. And so these are the addresses that we would use over and over and over in a private network. And this would be, again, that Class A. The next grouping is going to, so technically it's 172.16.0.0 through 172.31.255.255. This is our Class B private network. And what I would suggest at this level of instruction, just remember that 172 is going to be that range. So anything that starts with 172, I certainly would hope that in the testing that they wouldn't go as granular as having you know the full address range. But for the most part, just remember that anything in the 172 range is going to be your Class B private network. And then our Class C private network is any IP address in the range 192.168.0.0 through 192.168.255.255. And again, I would really hope that if you were asked to identify this range in the test, that they would mostly just kind of look at that first octet, that 192. While technically it is a much smaller slice of the 192 range, I would say that you'd be safe to just remember that our Class A private networks are going to be anything with the first octet of 10. Class B is going to be the first octet of 172, and Class C is the first octet of 192. Another range of IP addresses that we want to be aware of is the APIPA addresses. And so that's going to be any IP address between 169.254.0.0 through 169.254.255.255. So essentially you want to remember the first two octets, which is 169.254. So anytime that we see an IP address in the 169.254 range, that's going to indicate an APIPA IP address. Also, we have a loopback to localhost. That's the range 127.0.0.0 through 127.255.255.255. Now, typically on our Microsoft computers, we're going to see that the actual loopback IP address is 127.0.0.1. And what the loopback is we actually use this. We use this in troubleshooting networks So while we can ping other hosts, sometimes we want to we need to validate whether or not our where our network interface card is working properly. So let's say that we ping all of our known IP addresses on our network and outside of our network, and we don't get anything. Well, the question is the problem actually with our network interface card? So we actually use something called a loopback address. And so if you open the command line on your computer and ping 127.0.0.1, you're actually pinging your own network card. And the result of that ping will let you know whether or not your network interface card is actually working. And then the last range that I want to address in this video is the IP multicast range. And that's 224.0.0.0 through 239.255.255.255. So essentially, anything 224 through 239 on that first octet is going to be our multicast. And again, the purpose of that is that we're sending a single message out to multiple nodes at the same time. It would be very advantageous if you would have these ranges memorized, or at least be very familiar with kind of like how to work your way through these, because these are the ranges that you would not assign to a public IP address. Now let's talk about IP subnet masking on the IPv4. So here we have an IP address of 167.1.12.155.16. And so this is in our class B. So if we're using class full subnet masking, that's going to give us a default subnet, if you look right below that, of 255.255.0.0. And essentially what this subnet mask says is anything that's a 255, that's going to be kind of a locked octet for the IP addresses that we're going to give on this subnet. And anything with a 0 is going to be open for use. And so what I mean by that is, so if the IP address that we have for our network is 167.12.155.16 and our subnet mask is 255.255.0.0, what that means is that any IP address that we can assign in that range is going to have to start with 167.12. So 167.12 has to be part of any valid IP address in this subnet. If we assign anything that doesn't start with 167.12, it's not going to be part of this subnet, and it will not be able to communicate with the other hosts on this subnet. And so that's what that subnet mask is. Let's take a look at another one. So here we have, if 167.12.155.16, if we used a class C subnet mask for that. And so that would be 255.255.255.0. Then what that would mean is that every IP address in this subnet would have to start with 167.12.155. And so that's how that subnet mask works, is essentially the kind of just focus on the word mask. And what that word mask is going to indicate to us is so if we take our IP address for this network, and we're going to anywhere on that subnet mask where we have a 255, that it means we're going to have to use that IP, that number in that octet, and we can't use anything else. And so as we go from class A to class B to class C, there becomes fewer and fewer numbers that we can use as viable IP addresses in that subnet. So now we're going to take a look at IP address assignment. So one way that we can assign IP addresses to our computers is we can go in and use a static assignment. And what static means is that we're going to manually go in and and configure or set up these IP addresses. Now, this is absolutely something that can be done. It's something that had to be done on early networks. And that is you would go in and you would assign an IP address to that computer, and you would set up the subnet mask that it would use. You would set up the default gateway and the DNS server. And as long as you have just a few computers, it's not really that big of a deal to go in and do that. If you've got 2 or 3 computers, it's pretty easy to keep track of it. But as you start adding computers and as those computers get replaced, now it becomes very burdensome to remember which computer had which IP address. And then let's say, for instance, that we start using a different DNS server. Now I've got to go through and I've got to change that setting on all of the computers. Additionally, one of the issues that we have with IPv4 addresses is we were running out of addresses, and so one of the things that would come up is we would be assigned just a handful of IP addresses. And so let's say if we've got 4 computers, then now we're going to need 4 IP addresses. But so what happens if, let's say that this is a day shift and a night shift. So 2 of the computers are being used during the day and 2 of the computers are being used at night. But because we assigned these IP addresses statically, all 4 of our IP addresses are being used. And so if we wanted to add another computer, we'd have to go and purchase another IP address. And so obviously there's a lot of reasons why static IP addressing is problematic. And so we actually there was something devised called DHCP. And so the DHCP, what it is it's we're using a server to assign different parts of the IP configuration. And what we can do is the scope of the DHCP is we can actually assign a range of IP addresses, and we can set up that range. We can assign an appropriate subnet mask. We can assign the address of the DNS server that computer should use, and we can assign the address of the default gateway that computer would use to get out of our subnet. And the way that the DHCP assignment works is, so if you look here, going from bottom to top, so the computer comes online. We see the computer on the left and the server on the right. So this computer comes online, and it does not have an IP address. So the first thing it's going to do is it's going to send out a DHCP discover, or it's basically just going to it's going to call out on the network and say, hey, is there a DHCP server available? And then what's going to happen is we see right above that we have the DHCP offer, and the server is going to respond to that request and say, yeah, I am a DHCP server, and I can help you out. What do you need? And so then above that we'll see the DHCP request, and essentially what that is the computer making a request to the server for an IP address. And then the server is going to respond, and it's going to say, here's your IP address, and you can, it's going to give it a lease time. So, it'll give it an IP address and say, you can use this IP address for 3 days, and then you need to surrender it and ask for a new one. And so that's basically how that DHCP assignment works. Now, one of the things that can happen with IP address assignment is where our DHCP router our DHCP server is on our network. And so, like when a host comes online, it's going to make that request. Well, that request is only going to be broadcast inside of its own subnet. And so if the DHCP router is, as we see this gray one, if it's inside that that subnet, that's not a problem. That DHCP router can easily assign that IP address to the host. Now let's say that the DHCP router goes offline, or we move it outside of the router, as we see with the blue one on the right-hand side. So now we have a router between our hosts and our DHCP server. So they're not on the same subnet. And so what's going to happen is when that host comes online, or when the lease expires on its IP address, it's going to send out the request, but that request is only going to go out inside its own subnet, which means it's not going to cross the router and it won't reach the DHCP server. And so one of the problems that we might have on our network is if we've installed a new router, or the router wasn't set to forward the DHCP request to the server across the router, then those hosts are not going to be able to receive a IP address assignment. Now, if we do have a problem where, again, just like the last slide, where we have a router in between our hosts and our DHCP server, or if for some reason the DHCP server just goes offline, the hosts are going to fail over into something called a PIPA. And what this is so if we remember back to our networking fundamentals, every computer that's on a network requires a network interface card and an IP address to be able to communicate on the network. So if it doesn't have a static IP address and it can't reach a DHCP server, it's going to say, well, I need something. And so what we have is the range of IP addresses from 169.254.0.0 through 169.254.255.254. These are reserved for our APIPA IP addressing. And essentially what's going to happen is, so either that computer is going to come online or the lease is going to expire and it can't get an IP address, it's going to choose for itself an APIPA address and it's going to broadcast that out on the network and say, hey, is it okay if I use this address? And so what we would see is now all of the hosts that are on that subnet that don't have a DHCP server, they're eventually all going to end up with APIPA addresses. And so when you're troubleshooting a network, if you have problems with all of the computers not being able, they can reach each other, but they can't reach any other resources on the network or get out of the network. The first thing we could do is run an IP config on that computer, and if we see that the IP address for that computer starts with 169.254, that tells us that we have rolled over to APIPA and we have a problem with our DHCP connection to our DHCP server. So now what we see here is a situation where so the connection to the DHCP server is lost for some reason. Either the DHCP server has gone offline or just for some reason we can't reach it. And so we see that computer A, obviously, it must have had a lease that hasn't expired yet, so it still has a valid IP address in our subnet. However, B and C are now on the 169.2.254 address, or the APIPA addressing range. And so what we can assume from this is either they had been offline and just came online and were not able to get an IP address, or their lease is expired. Now, in this situation, computers C and B would be able to talk to each other, but they wouldn't be able to talk to A or to any other resources on the internet, and they wouldn't be able to, or on our subnet, and they wouldn't be able to get out to the internet because they wouldn't be able to reach our default gateway because they're on the 169.254. And typically, our default gateway is going to have a static IP address that's not going to be in the APIPA range. And so as we can see here, this would cause a lot of problems because as these computers start to fall into the APIPA addressing, they're going to lose connection with the rest of the network. All right, so now moving into our IPv6 addressing, some definitions that we want to take a look at is multicast. So again, a multicast address is one that we use to send out the same message to multiple hosts at the same time. Not all hosts, that would be kind of our broadcast, but we can. We'll see that there is a multicast IPv6 address. Also, we have a local loopback. So just like we had on our IPv4 network, one of the things that we might need to do in troubleshooting the network is to determine if our network interface card is working on our computer. And so for that, we would use our local loopback address. And in the IPv6 configuration, that's going to be 0.0.0.0.0.1. Or we can abbreviate that as : 1 or : 1/128. And that is, we don't assign that to any other interface. That's just something that we use directly on to check our network interface card. Also, the term dual stack. Dual stack indicates that that our network is set up to handle both IPv4 and IPv6 addresses on that. And typically, if we have a dual stack, that means that each host or each computer is going to have an IPv4 and an IPv6 address assigned to it. And then tunneling. Tunneling is where we have we're using one of our IP addressing protocols and tunneling through the other. So right now we're kind of like in between the transition between IPv4 and IPv6, and so we have some networks and some subnetworks that are on IPv4 addressing, and then some that are on IPv6. And so tunneling is anytime we're moving through one range through the other. So say that we have two networks at a home office and a satellite office that are both on IPv6 addressing, and we need to go through our metropolitan area network that is still on an IPv4 addressing. So we would actually be tunneling through an IPv4 infrastructure on our IPv6 network, and so that's how tunneling works. IPv6 addresses look a lot different, and the reason that we needed to make this switch is so if we look up at the top, we see that IPv4, the 32-bit address, gives us 4.3 billion addresses. Now that might seem like a lot, but then if we start looking at the fact that there were certain ranges of IP addresses that we had designated for different things, and not only that, but now each individual person probably has multiple IP addresses because that's gonna so your home computer and your cell phone and your laptop computer and your tablet, and let's say that you have an internet enabled thermostat, and so that's going to need an IP address. So we see that very quickly with this proliferation of Internet of Things and mobile devices, 4.3 billion IP addresses is not a lot for a worldwide interconnected network. And so now we have IPv6, and that gives us 34 to the 10 or 34 undecillion possible combinations. And if you saw the video that I showed earlier in this course, basically what that is we could give an IP address to every grain of sand on the planet and still not run out. And so that's the reason why we had to switch, is we were running out of IPv4 addresses. Now let's take a look at the formatting. So the formatting of the IPv6 address is we're going to have 8 blocks of 4 characters. And I'll kind of explain because sometimes we don't always see 4, but the full expanded IPv4 or IPv6 address is going to have 8 blocks of 4 characters separated by colons. And those characters are going to be in what we call hexadecimal notation. And so what that means is each character in that block can be 0 through 9 or A through F. And so as you see, like that first block there, we have FEC2. That is a valid block in an IPv6 notation because it contains either 0 through 9 or A through F. Now, one of the things that we can do with IPv6 is because it is so long, and early on, as we're starting to assign these, there are actually a lot of zeros that come up in this. So as you see in that fifth block, what we've actually done is we've gone from 08CA, and we've written it as 8CA. And so the reason is because with our IPv6 addressing, we can abbreviate it by eliminating any leading zeros in each of the blocks. And what that means is, so if it starts with a 0, you can just negate the zeros until we get down to a non-zero integer or digit. Another thing that we can do is anytime that we have several groupings of zeros, we can abbreviate those by indicating with a double colon. So if you look down at the bottom, you see that we have FEC2 and then a double colon and then 8CA. And essentially what we've done is we've taken those 3 groups of 0 and we're not writing them out or typing them out anymore. We're just using a double colon to indicate that everything between those 2 colons is a 0. Now, if you remember, one of the things that is very important is we can only do that once. If you look back behind you, you see that there's another set of zeros in there, but we couldn't abbreviate that one because if we did, there wouldn't be any way to know how many sets of zeros are in each abbreviated section. And so again, a valid IPv6 address is going to have the fully extended IPv6 address is going to have 8 blocks of 4 hexadecimal characters. And then we can abbreviate those blocks individually by eliminating any leading 0 character. And then anytime we have groupings of zeros, we can abbreviate those groupings by with a double colon, but we can only do that once. The reserved IPv6 address ranges, as I said, we have that loop back to the local host, and that is 0.0.0.0.0.0.0 or I'm sorry, 0:0:0:0 all the way on. And basically what it is it's all zeros, and then the very last the very last digit is a 1. And that is the loopback IP address in IPv6, and we would use that to test the network interface card on the computer we're at. And then we have a multicast address. You're going to want to remember this one as well, and it is FF00 double colon, and then all the way to the end. And basically what it is it's all zeros after that, and that /8 means that it's subnet masked to the last 8 binary digits. And so essentially what it is it's FF00, and then all zeros after that would be our multicast address. Again, IPv6, if we have a dual stack, what that means is that we would probably have, now it shows here an IPv4 server and an IPv6 server. Typically what would happen is we would actually just set up the IPv4 scope and an IPv6 on the same DHCP server, but it would assign an IPv4 and an IPv6 address to each of our hosts. And then again, this is just kind of a visual representation of tunneling. So we see over on the left, we have an IPv6 subnet, and over on the right, we have an IPv6 subnet. And then it needs to move through an IPv4 network. So we package it and tunnel it through that network, and then it comes back out as IPv6 on the other side. So this would be a 6 to 4 tunneling. We also could have a 4 to 6 tunneling, which would be a IPv4 through an IPv6. And there's a couple other tunneling protocols that we could use, but really for the test, you just need to understand what tunneling is and what it does. All right, so that is the presentation for Understand IPv4 and Understand IPv6.